Okay, good morning. Assalamu alaikum, guys. Welcome back to grade 12 chemistry slash physics. Fine, teens, where in today's lesson we're going to be continuing with organic chemistry, right? Yeah, we're going to be continuing with this past paper and then we'll try and go into organic reactions. Okay, just to confirm, you guys can hear me clearly, right? And you guys can see my screen and see me as well. Perfect. Okay, hope you guys are having a good holiday. For those of you who are joining in the holiday, well done to you. Let's continue. So, if I'm not mistaken, from what it looks like anyway, we did till 2.2.2, but nevertheless, let's redo both of them, right? Let's look at this question from November 2021, and it's basically a very, what do you say, it's a very, common, it's a very, what's the word I'm looking for? I have no idea. But this is a regular setup for organic chemistry in the examinations, right? If you've done many past papers, you'll know that, okay? So let's have a look through it and let's see if we can answer the questions. So the letters A to H in the table below represent 8 organic compounds. 2.1, define the term unsaturated compound. So remember we said saturated single, so unsaturated, a compound that contains a double bond or multiple bonds and does not contain only single bonds. A compound that contains a double bond, okay, and does not contain single bonds. So exactly what we said. Saturated is single, so unsaturated is 2 or more, double or triple or quadruple, etc. Okay, 2.2.1. So 2.2, write down the 2.2.1, write down the letter that represents an unsaturated compound. So we were basically looking for a double bond existent between carbon atoms, okay? So in that case, we said B or E. Again, A was out because A was between the oxygen and the carbon. We are talking about between two carbon atoms. So in this case, we can clearly see that B, okay, has a double bond between two carbon atoms. But what's not so clear is E. Okay, you'd have to know it as well, because what if in another exam paper they just asked, they just gave you E, okay, and you have to choose E. Okay, so you need to be able to be comfortable with knowing that E is a correct option as well. Why is E a correct option? E is a correct option because it is the general formula for an alkene. Okay, the general formula for an alkene, which is C2H2N. So that's where we get C2H4 from. Okay, and yes, it's an alkene which has a double bond, which is also an unsaturated compound. 2.2.2, they said name the functional group of compound C. And after drawing it, okay, we did some analysis of how should we draw from a semi-condensed structural formula to a structural formula, or semi-condensed formula to a structural formula. How should we draw it? So we take the approach of drawing it carbon by carbon, and understanding that in between what is attached to these carbons, okay, and then drawing it accordingly. And after drawing it, we deduce that this is actually an aldehyde, okay, and since it's an aldehyde, if we go back here, right, we said that an aldehyde, sorry, we said it was a ketone actually, not an aldehyde. An aldehyde is the one that has it on the edges. The ketone has the double bonded oxygen to the carbon in the middle somewhere. Okay, so an aldehyde, okay, and sorry, a ketone's functional group is known as a carbonyl. Okay, so that's what we said, ketone, and our answer is carbonyl because that's the functional group. Yeah, that's the functional group of the ketone. 2.2.3, the letter that represents a chain isomer. Okay, the letter that represents a chain isomer of compound C. So what is compound C? Compound C is this guy. So of course, no matter what, right? If you have semi-condensed, if you want to answer a question, just throw it out in instruction, it will make a lot more sense. Okay, so they want a chain isomer of compound C. So let's just revise some things which are important, right? If they want a chain isomer, Firstly, we stay in the same homologous series, so we are not changing homologous series. Now, what is a chain isomer? Different number of branches on the main chain. The branches are different positions, minimum 4 Cs. Example, pentane changes to 2-methylbutane. So when we had pentane, originally we had 5 carbons in the main chain, but a chain isomer of it could take one of those 5 carbons out of the main chain and create a group with it. And in that case, you'd still have the same amount of carbons, same amount of hydrogens, okay, but it would be known as a chain isomer. So let's continue. Okay, so any idea? A letter that represents a chain isomer of compound C. So we are looking for a compound that still has 5 carbons, but perhaps one of them, because I think for chain isomer you have to have minimum of 2 Cs. No, I mean 4, I was going to say. I don't know. But yeah, what could be seen as a chain isomer of compound C? Anyone who has any guesses or answers or calculated guesses? Okay, F is a good shout. Okay, so firstly, compound C is a ketone, right? So the first thing we can actually look out for is, are there any other ketones, or which are the other ketones? Because remember, with a chain isomer, you don't change the homologous series, so you're keeping within ketones. Okay, so you're going to look, I would say that's the first step at least. You look for another compound that's a ketone. So here, that's not a ketone. That's not a ketone. Not a ketone. This is a ketone. Wait. Is this a ketone? 5, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, it's not a ketone. E is not a ketone. G is not a ketone. H is not a ketone, but F is a ketone. But we can also confirm it, right? If we look at bute is the prefix for 4. So this has 4 carbons, and it has 1 methyl, not 3 methyls. 3 is just a position. It has 1 methyl for 1 extra carbon. And in total, they make 5 carbons. Okay, so therefore, this is definitely a ketone with 5 carbons, but it just has a branch, and therefore it's a chain isomer of C. Okay, let's look at 2.2.4. Give the IUPAC name of compound G. The IUPAC name of compound G. Okay, I want you guys to try this out. We want to give the IUPAC name of compound G. IUPAC name of compound G. If you like, I'll give you guys like a minute or so. Five dichloro-3-methylhexane. That is a good answer. I'll wait for maybe one more person to give an answer, then we can continue. Okay, so same as everyone, perfect. Okay, so let's examine it. So what are the steps to naming? Let's revise that really quickly. So naming consists of the following. You have to know your prefixes and your suffixes, of course. So first step is to identify the longest carbon chain, okay, the longest possible carbon chain. That's the first thing. The second thing is numbering, so you have to number it. Okay, so you start closer to a double bond or closer to a triple bond. That's your first criteria. If you have no double or triple bond, or if they equidistant from one another, you start labeling from the side that's closer to any group. But our groups, they are our groups. Okay. And then for the third one, okay, if you don't have any closer groups, or if there's no groups, so if they're equidistant, you will put it in alphabetical order. Okay, that's if everything above is equidistant. That's why equidistant is written in brackets, and that's actually the order in which they'll go. Okay, bromo, chloro, ethyl, fluoro, iodo, methyl. Okay, then let's talk about naming. So now once we've numbered it, now we can name it. So the way you name it is always halogens. Halogens go first if you have halogens. Then your ethyls go second if you have ethyls. Then your methyls go third if you have methyls, and then your parent. Okay, in parent, within your parent, you have to indicate the position of the functional group. In fact, for all of them, you have to indicate their position. So between two numbers, you have commas. Between a number and a letter, you have a dash, as can be seen here. Okay, and so once we numbered this guy, we started naming it. So we could see that there's an ethyl on group number 6. So we said 6 ethyl, 6 dash ethyl. Dash again, we could see 1, 2, 3 methyls. So we labeled, we named them 2, 4, 4. So if they're at the same place, you put the 4 twice. Trimethyl. So however many groups you have, you're going to put another prefix in front for the groups. 2 is di, 3 is tri, 4 is tetra. Okay, and then we're done with that because there was no halogen, so we just did ethyl, methyl, and then the parent. Okay, so the parent in this case, it was an alkene with 8 carbons, and it had 2 double bonds. So we definitely indicated the position of the double bonds in the IUPAC name. 2-2, 5- Number 1 is indicate the position of the functional group. Number 2 is you can also add the prefix. Okay, if you have 2 functional groups, you could di or tri or tetra. So that's how we name, right? Let's get back to the question. And let's name this guy. So firstly, identifying the main carbon branch. This one's a bit easier because it's all in a straight line. If I try going that way, it's going to be much less than if I go straight. So I definitely am going straight. And when I go straight, I can see that there's 6 carbons in the chain. Okay, so now where do I start labeling from? Okay, I start labeling from the side with the closest group. See, I already forgot. The first one was double or triple bond. Actually, there's no double or triple bond here. Okay, then the second one is closer to any group. So if I look here, I have a chlorine that's on the second carbon from the left. Then if I look here, I have a chlorine again. It's also from the second carbon from the right. So that's equidistant. So I don't yet move on to the next one because I have another group. This is a methyl group. And if we count, it's from the left, it's 1, 2, 3, the third carbon. And from the right, it's 1, 2, 3, the fourth carbon. So therefore, the closest group is actually towards the left. So then we label from the left. 1, 2, 3, 4, 5, 6. Okay, so now we know the position of everything. So let's label. Remember, halogens, ethyl, methyl, parent. Halogens, ethyl, methyl, parent. There's no halogens, there's no ethyl, there's only a methyl. Oh, sorry, there are halogens, my bad. These are our halogens. Chlorine, so we name our halogens first. Okay, so the halogen is on the second chlorine and on the fifth chlorine. So we're going to say 2,5 dash dichloro. Why dichloro? Dichloro because there's 2 chlorines. Dash again because we're going to put a number. Number of what? Halogens, then ethyls, then methyls. So there's no ethyls, but there's methyls. So it's on the third carbon. So dash methyl, 3 dash 3 dash methyl. Then the parent chain, which in this case is hex, the prefix, because there's 6. And it's a haloalkane. So it's an alkane. So you're going to say hexane. Okay, so I hope that makes sense. IUPAC name of compound G, 2.2.4. Okay, we just did that actually. general formula of the homologous series to which compound E belongs. Okay, we already kind of did that. Okay, remember compound E belongs to alkenes. So you see why it's important for us to know the general formulas. Okay, they look a little something like this. Okay, so each one is a general formula, right? Just telling you generally how to calculate the amount of carbons and hydrogens in a certain organic compound. So CnH2n plus 2, CnH2n, CnH2n minus 2, and so on. General formulas. Okay, so we have to know the general formula of it so that we are able to identify it. So in this case, we can basically just see that alkane is C2H2H4, so it's clearly 2 times the amount of carbon. So this is CnH2n, and that is for alkenes. So the general formula to which alkenes belong to would be CnH2n. Okay, let us look at the 2.3. Define the term functional isomers. Okay, so you get 3 different definitions technically, right? Let's go back to our isomers. You get 3 different definitions technically. I only gave the one for structural, okay, which is I only gave the general definition, which is compounds that have the same molecular formula but different structural formula. Now this is true for all isomers. However, you can specify, okay, how are they structurally different for each one. So for example, if they had to ask you define a chain isomer, you would say, okay, compounds that have the same molecular formula but the different amount of carbons on the main branch, okay, or different amount of so compounds that have the same molecular formula, but I would say same molecular formula and you don't have to say same amount of carbons and hydrogens altogether, because I suppose that's indicated by molecular formula. So same molecular formula, okay, but different structural formula. So if you're dividing chain isomers specifically, different amount of carbons in the main branch, alternatively, different amount of branches. Positional isomer, compounds that have the same molecular formula, but have different positions of the functional group. Okay, functional isomer, compounds with the same molecular formula, but different functional groups. That's how they define. So that's why I didn't write each individual definition, because they're easy, right? You just define it in terms of each respective isomer. So isomers in general, compounds that have the same molecular formula but have a different structural formula. Compounds that have the same molecular formula but a different structural formula. Compounds that have the same molecular formula. Yes, okay, so then for chain, like I said, I'm going to repeat them again. Specifically, you'll say compounds that have the same molecular formula, okay, but different amount of carbons in the main branch, or different amount of groups in the from different amount of what you call them? Branches. No, yeah, branches. Okay, for positional isomers, compounds that have the same molecular formula but a different positional functional group. For functional isomer, compounds that have the same molecular formula but different functional group. Okay, again, the definition specifically for each one. Let's continue. So yes, that's the definition. 2.4, for compound A, write down the homologous series to which it belongs. Okay, tell me, compound A, what does compound A, what homologous series does compound A belong to? Anybody, someone tell me. No, not an ester, no. Close to an ester. It's actually a carboxylic acid, correct. We can see by the Cu, okay, the C double bonded to the O and then bonded to an OH, which is Cu in semi-structural formula. Okay, this is actually a carboxylic acid. Okay, let's look at 2.4.2, the structural formula of its functional isomer. The structural formula of its functional isomer. Okay, I want you guys to give this a go. I'm going to give you guys like a minute or so. So at 22. The structural formula, or like maybe a minute now. The structural formula, basically, the structure, this is a structural formula, right? Remember, we went through the different types of formulas of its functional isomer. So just to remind you, carboxylic acid, okay, can become an ester. Its functional isomer is an ester. Okay, so there's your hint. Okay, so you're converting from carboxylic acid to ester. Also, another hint for ester, your functional group is Cook, right? C double bonded to an O double bonded to another O and a C. So we want to draw the structural formula for its position, functional isomer. Okay, let's mark it or let's do it. So firstly, this is a carboxylic acid with 2 carbons. So all we need to do, remember, in all isomers, the molecular formula stays the same, meaning the amount of carbons and the amount of hydrogens remains the same. So if there's 2 carbons in the carboxylic acid, in order to draw its functional isomer, the structural formula of its functional isomer, we just need an ester that has 2 carbons. An ester that has 2 carbons. How do you draw an ester? How do you draw anything? You always start off by drawing the functional group. Now, if you look at this functional group, you'll notice that the functional group itself has 2 carbons, and that's the max we need. So we just close it off. Here, I fill the carbon because it has 1 extra space. I fill it with a hydrogen, and I fill this with 3 hydrogens. This is a CH3. So this is an ester with 2 carbons. Okay, just for interest's sake, I always split it there. The side that comes from the oxygen comes from the carboxylic acid. This comes from the ester. Sorry, this comes from the alcohol. So this would be called methyl methanoate. Okay, 2 carbons in an ester. Okay, compound D undergoes dehydration reaction. We don't care, we still didn't get there. Let's look at question 3. The melting points and boiling points of 4 straight alkane chains are shown in the table below. Okay, so remember, these are to do with the experiments that we discussed. Let's just see if we can brush over them. Okay, we discussed all of them which affect the boiling point or the melting point. The independent variables differ. In one, we change the molecular size. Okay, in one we change the homologous series, and in the other we change the number of branches, and we see how it affected the melting and boiling points. Okay, so the melting and boiling points below are 4 straight chain alkanes are shown in the table below. So we have pentane, hexane, heptane, and octane. Okay, so define the term melting point. That's it. That's a forgotten one. Basically, excuse me. So basically the definition for melting point is the temperature at which solid and liquid phases are in equilibrium. Okay, the temperature at which solid and liquid phases are in equilibrium. It should be in your examination guidelines. Let's look at 3.2. Write down the general conclusion that can be made about the melting points of straight chain alkanes. Okay, I want you guys to tell me, give this a go. Tell me what do you think for 3.2. What would we say a general conclusion is that could be made about the melting points of a straight chain alkanes? Okay, so these are all straight chain. They are comparing. Okay, answer the question and I'll go back to the next one. Okay, I'll give you guys an answer. So what we could say for this, okay, is basically, if we look at it, right? Okay, so before we discuss that, let's discuss which experiment we're dealing with. So we have alkanes. They all are alkanes and they're straight chain. So we know it's not the chain experiment because they're all straight chain, right? They don't, there's no branches to them. Okay, and they are alkanes. So the homologous series is being kept constant. So if we have to look at this one changes homologous series, so it's not that one. This one changes branches, so it's not that one. We're dealing with molecular size. We're dealing with staying in the same homologous series, having the same structure, okay, and positional functional group, right? And we are comparing within a certain homologous series, okay, where we only specifically mention London forces, okay, between the compounds. Okay, so where are we? Let's do this. Okay, so a general conclusion, right? Let's see if we can see what's happening to the trend. So you want to identify what's the trend, what's happening to the melting points and boiling points as we are changing compounds. So pentane firstly has 5, 6, 7, and 8. So as we go down, we're increasing the amount of carbons. So that's your first part of your conclusion. You're going to say, as carbons are increasing, and then let's identify what's happening as carbons are increasing. So the melting point for pentane is negative 30, then it goes to negative 94, then it goes to negative 96, negative 57. We can see that it's getting bigger. Even from 36 to 69, 98, 125, it's getting bigger. So the more carbons you add, essentially, the higher your melting and boiling points are going to be. So write down the general conclusion that can be made about the melting points of straight chain alkanes. So you can say, the more carbons in a straight chain alkane, the higher the melting point. That's it. Okay, alternatively, okay, so for when you have these general conclusions, or sometimes how do they phrase it, like in biology, and that do they ask for relationship or something? But for these, you always want to identify your independent variable and your dependent variable and mention them, okay, and mention their relationship. So you could even say that, yeah, all right. So you could even say as the chain length increases or as the number of carbon atoms increases, okay, the melting point increases as well. Okay. Number 3.3, name the type of van der Waals forces that between the molecules of octane. So remember, this page just contains all the forces of all the homologous series. So alkane forms under the hydrocarbons, only hydrogen and carbon, and alkanes contain London forces only. Right? So let's have a look. Okay, so the type of van der Waals forces between molecules of octane, London dispersion. 3.4, write down the predominant phase of the following alkanes at negative 100 degrees. Choose from gas, liquid, or solid, pentane and octane. So let's look at pentane. At negative 100 degrees, Would it be gas, liquid, or solid? What do you guys think? Okay, this one requires a bit of thinking. At negative 100 degrees, okay, is pentane in gas, liquid, or solid phase? Any definite answers? Okay. Okay, we have a liquid. Okay, so let's see how do we answer this, right? So what you do is you have to basically fit 100 degrees into here, negative 100. Where does negative 100 fit? Okay, so is negative 100 smaller than negative 30? Is it between negative 30 and 36? Or is it after negative 36? That's all you have to determine. So negative 100 is actually after negative 130, but before 36. So then you can tell yourself, okay, just say the temperature is negative 140, okay? And then it rose up to negative 130, and we know for sure that pentane melted, okay? Pentane melted because we reached its melting point, we reached its melting point temperature. So pentane has melted, so it went from being a solid to a liquid. Definitely. Once it reached negative 130 degrees, it became a liquid. And then the temperature increased and increased and increased until it got to 36. But before it got to 36, negative 100 is between negative 130 and 36. So it has melted, but it has not boiled yet. So it melted from a solid to a liquid and it didn't boil. So it's a liquid. What about octane? Okay. Octane at negative 100 degrees. What are we saying? What do we think? Solid, liquid, or gas? Okay, solid, good. So we basically have to fit in negative 100 here. So negative 100 goes before here, for sure. It's smaller than negative 57. So it hasn't even reached its melting point. Okay, so if something hasn't melted, what would it be? It would be a solid. Because in order for it to melt, it needs to be a solid, which melts into a liquid, which then becomes gas at some point. It boils. Okay, so in that case, this guy is still a solid. Okay, 3.5.5. Hexane is now compared to 2,2 dimethylbutane. Hexane is now compared to 2,2 dimethylbutane. Is the molecular mass of hexane greater than, less than, or equal to that of 2,2 dimethylbutane? Is the molecular mass. Okay, so if you want to compare molecular mass, okay, between these two compounds, what we could do is just identify the amount of carbons and hydrogens there are in each, and then compare the molecular mass, because the molecular mass is made up by all of the elements. Okay, so if we have a look at what is it? Hexane, and alcohol has the general formula. What are we dealing with? Hexane or hexanol? Hexane. Okay. So we can see that an alkane, yeah, follows this formula: CnH2n plus 2. Okay. And then they had, so CnH2n plus 2. Oops. So let's go back to the question and let's answer it. So hexane is now compared to that. So if we look at hexane, okay, hexane CnH2n plus 2. So it's C6H2 times 6 plus 2, which is C6H14. Okay, that C6H14, that is the molecular formula for hexane. Why am I getting the molecular formula? Because that's going to tell me how many carbons and hydrogens I have in order to tell me what my molecular mass is. So 2,2 dimethyl butane. Remember, butane has 4 carbons. So it's C4H, 2 times 4 plus 2 is 10. But it's also 2,2 dimethyl. So it has 2 CH3s, CH3, CH3. It has 2 CH3, so CH3, CH3. So therefore, when we combine this, we have C6H. What is it? CH5 maybe? No. One connecting was 2, I guess. Okay. So we get basically C6H14. If you had to draw it out, you'd count it and you'd see that you have 6 carbons and 14 hydrogens. Give a reason for your answer. Because they have the same molecular formula, okay? They have the same number of carbon and hydrogen atoms, okay? So let's look at 3.5.2. Is the boiling point of 2,2 dimethyl higher than, lower than, or equal to that of hexane? What do you guys think? Higher than, lower than, or equal to that of hexane? Lower than. Okay, so I would say lower than as well. Okay, the boiling point of 2,2 dimethyl butane is lower than that of hexane. Why would we say that? So remember, we're going to compare their structures, right? These are 2 chain isomers. When it comes to chain isomers, okay, it's like the chain question as well, the experiment, I mean. Okay, mention about London forces. Only as the number of branches increases, the surface area decreases. London forces become weaker. Compound A has the, okay, more energy required to overcome attraction forces between, excuse me. More energy is required to overcome the attraction forces between compounds. So that's exactly what we could mention. Okay, so when we're going to compare hexane and 2,2 dimethyl butane, we're going to say, even though they have the same molecular formula, they are more branched. 2,2 dimethyl butane has more branches compared to hexane. Okay, then we can talk about the surface area. We can say that higher branches equals to less surface area, which requires, what is that? Let's go back. Here the surface area, as the number of branches increase, the surface area decreases. We can say exactly that. Okay, then we can say the London forces of, so now we want to compare them exactly to each other. We say that the London forces of, sorry, wrong page. The London forces of 2,2 dimethyl butane are weaker than that of hexane. Okay, and then we can say that therefore less energy is needed to overcome or break the intermolecular forces. So we mentioned where we give the answer, I suppose, then we compare them. I hope that makes sense. Let's look at the next one. Is the boiling point of 2,2 dimethylbutane? Oh, we just answered that, and we just answered the fully explain your answer. Okay, and then for that, the last step, don't forget, less energy is required to overcome the intermolecular forces. Okay, so I think that's that question done. Let's go ahead and just start off with reactions. We can do some basics before we do reactions. Okay, so primary alcohol, secondary alcohol, and tertiary alcohol we discussed. Let's revise it quickly. So basically, primary alcohol states that a primary alcohol is the carbon that's bonded to the OH. Okay, the carbon that's bonded to the OH. How many other carbons is it attached to? In this case, it's just simply one. Okay, so since it's one, that's why it's a primary alcohol. Secondary alcohol, the carbon that's attached to the OH, it's attached to two other carbons, and it's known as a secondary alcohol. Then we have tertiary, of course, the one that's attached to the OH. Okay, yeah, it's attached to 2, yeah, it's attached to 3, and that we refer to as a tertiary alcohol. Let's look at some physical properties. Boiling point, melting point, viscosity, vapor pressure, flammability, volatility, and solubility. So, boiling point. Okay, what is boiling point? Okay, boiling point refers to the temperature at which the vapor pressure of a liquid is equal to the external atmospheric pressure. Then we have melting point, the temperature at which we actually, this is a wrong definition. This is a very basic definition. We should use the other one, the temperature at which I think it's solid and liquid, solid and liquid are in equilibrium, something like that. We just went through it earlier. Let's see if I can find it. Temperature at which a solid and a liquid phases are in equilibrium. Okay, viscosity, a liquid's resistance to flow. Vapor pressure, the pressure exerted on the surface of a liquid by the vapor. Okay, so the first, what is it, 3 are directly proportional to the intermolecular forces, meaning, okay, what does it mean if they're directly proportional to the intermolecular forces? As these increase, that means that intermolecular forces will increase. So as molecular forces increase, these prices, these not prices, these properties would increase as well. Melting point, boiling point, and viscosity. Okay, then we look at inversely proportional. So vapor pressure, okay, as intermolecular forces decrease, these would increase, and as intermolecular forces decrease, these would increase. So did I say the same thing over and over? As one would decrease, the other increases, and as intermolecular forces increase, this would decrease. Did I just say the same thing 3 times? Okay, basically, listen, intermolecular forces increase, vapor pressure decrease, intermolecular forces decrease, vapor pressure increase. Doesn't have to be as confusing as I made it, but yes, okay, so that's important to note, right? And it kind of makes sense, right? Because directly proportional to intermolecular forces, right, they're the bonds that keep these compounds together, okay? So if these bonds that are keeping these compounds together become stronger, then naturally the boiling point, is my camera off? It stops working. Okay, so then naturally the boiling point, which is it's basically boiling point is like the point at which, right, you're converting to a gas. Okay, so it needs energy, and if the bonds are stronger, then the boiling point, it's going to take a lot more temperature and a lot more energy to break or overcome these forces. And same with melting point, similar to with viscosity. High both vapor pressure, it's inversely proportional. Okay, so those are key things to know. Okay, so I have these reactions, organic chemistry reactions. I do plan to rewrite them so they're a little more structured at some point, and I'll give them to you guys. But the basic understanding we can still get from here, which is a little bit of a mess, but nevertheless. Okay, so we discussed saturated compounds, which are only single bonds, alkane, haloalkanes, and alcohols. Okay, these are saturated because saturated single. Unsaturated double or triple. Example is an alkene. Okay, So we have three different types of organic chemistry reactions. We have substitution, we have addition, and we have elimination. Substitution, addition, and elimination. So a substitution reaction, okay, is when you go from a saturated compound to another saturated compound, saturated to saturated. Addition is when you go from unsaturated to saturated, and elimination is when you go from saturated to unsaturated. So sat to sat, unsat to sat, and unsat to unsat. Okay, so let's have a look at our first few substitution reactions. Okay, so our substitution reactions, the first of which is an alkane plus a halogen, which gives us a haloalkane or a haloalkane plus a halide. Okay, so firstly a halide. Okay, we'll get to what a halide is. So basically, substitution is like in soccer when they have a substitution. You take one guy out and you put one guy in. That's basically it. So we have an alkane, whatever the alkane is, butane, hexane, whatever the alkane is, you add it to a halogen, okay? And what will happen is that that halogen will replace one of the hydrogens inside of the alkane. Okay, the halogen will replace the hydrogen inside of the alkane. So we have CH4 plus the halogen should give us the haloalkane plus halides. Halogen is Cl2, okay, or I2 iodine, or F2 fluorine, okay, and they could be named according to whichever halogen you use. If you use chlorine, chlorination. If you use iodine, iodination, I guess. If you use fluorine, fluorination, etc. Okay, and as you can see, one guy gets substituted in, and that extra hydrogen, what it does is, because chlorine is diatomic, okay, it has an extra chlorine which bonds to that lonely H, and we have HCl, which is known as halide. Halide is a hydrogen plus a halogen. Okay, let's look at number 2. Okay, let's not look at number 2. Let's call it there, right? When I'll let you guys off a bit early. It is holidays, 2 minutes. It's not that great of a deal, but it's okay. Just take what you get. But yeah, we'll go through this properly next week. We'll go through each of them, substitution, addition, elimination, do examples, and then we should be done. Okay, so let's call it there. Hope you guys enjoyed the lesson and enjoying your holidays. All the best. Good luck, I guess, for holidays. I think you guys starting again soon in about a week or 2. But yeah, I mean, either way, Jazakallah khair. Thank you guys so much for joining. All right, I'll see you guys next week, same time, same place. Inshallah. No problem, I mean.